It makes sense that we're going to begin with a discussion of light, because astronomers are at a disadvantage compared to other scientists. We can't pick up, touch, smell, lick. That's kind of gross. We can't do hands-on activities with many of the objects in outer space because we just can't reach them because they're too far away. All we can do is look at them. Now, light is sometimes called an electromagnetic wave. So let's unpack that. In the word electromagnetic, we have electro, which should bring to mind electricity, and magnetic, which should bring to mind magnets. And the reason why light is called an electromagnetic wave is because it is produced by oscillating electric and magnetic fields that are traveling through space at 90-degree angles to each other. Light comes in the form of what we call a transverse wave. That's contrasted with what you might think of as like a slinky. A slinky is called a compression wave. The transverse wave or longitudinal wave is sort of like a rope being shaken up or down. And if you take a rope and shake it up and down, you're going to have high points, which might be a crest or a peak, and then a low point, which you might call a trough. And so we're going to measure different parts of this wave. The distance from peak to peak is what we call the wavelength. And depending upon how much you shake the rope, you're going to go a certain distance above the midpoint. The distance above the midpoint is called the amplitude. Wavelength is kind of easy to visualize. Frequency is not. If you look at a wave going by you and you take account of how many of these waves pass by you per second as it's moving, that's what we call the frequency. The frequency is the number of cycles or wavelengths that pass by an observer every second. And that's measured in a unit called a hertz, which has nothing to do with rental cars. A hertz is 1 cycle per second. And since cycle is unitless or dimensionless, we sometimes write this as 1/seconds. And if you'd like to get more of a visualization about what frequency is, I have a YouTube video that I recommend. Again, if you go to the actual narrated PowerPoint rather than the video, you can click on the link, and I start watching at about the 2-minute mark. Now, energy is carried by light. Light being an electromagnetic wave, electricity has energy, magnets have energy, electromagnetic waves have energy. So the energy carried by a light wave depends upon its frequency. And so the energy is proportional to the frequency. The higher the frequency, the more energy it carries. And this is what we call Planck's law. We're going to come back to this again because this is going to explain something that you might have noticed about different forms of light. Now, the relationship between the wavelength and the frequency is that for any given light, if you multiply the wavelength times the frequency, you end up with the speed of light. And the speed of light, which you probably heard of, is a very important constant in nature. It is denoted by the letter C, which you might think is very strange. It actually comes from the word celerity, not to be confused with celery. Celerity is sort of an old-fashioned Victorian word for speed that you only now see in crossword puzzles. So the speed of light in a vacuum is 186,000 miles per second, or 300,000 kilometers per second, or 3 times 10 to the 8th meters per second. Now, the speed of light is not something that is worth memorizing, but what you need to know and need to understand is that Einstein said that the speed of light in a vacuum is the fastest achievable speed in nature. So 186,000 miles per second is not only a good idea, it's the law. It's a law of physics. And this is sometimes called the tyranny of light speed. And the reason why it's called a tyranny is not only is it inconvenient for Star Trek, you can't go faster than the speed of light, can't even reach the speed of light, so it takes you a long time to get anywhere, which would be really inconvenient for Hollywood. but it also means that it takes light time to reach us from a distant astronomical object. And this is something that we call look-back time. If we look at the sun actually is the nearest star. The sun is about 93 million miles away. That's considered in our neighborhood, but it still takes light a certain amount of time to travel those 93 million miles. It takes about 8 minutes. So whenever we look at the sun, we are not seeing the sun as it is right now. We are seeing it as it was 8 minutes ago. Now, granted, the sun really hasn't changed in 8 minutes, but that gets you to start thinking about the fact that we're always getting old news. If we look at the nearest star system beyond our solar system, that's the Alpha Centauri system, that's 4.3 light years away. A light year is the distance that light travels in 1 year. So if we looked at Alpha Centauri tonight, we would be seeing it as it was 4.3 years ago, not as it is right now. Now, granted, it probably hasn't changed much in 4.3 years, but now let's look at things that are much farther away. Let's look at a galaxy, and let's imagine that this galaxy is 2 billion light years away. That means that that light has taken 2 billion years to reach us. So we are seeing it as it was 2 billion years ago. Some of those stars that we see in that galaxy are no longer there. They've died. That's why it's the tyranny of light speed. You're never actually seeing now. You're always seeing old news.